Yes. Started. Get started. Okay, answer your names, please. Amo. Lassie. I think that's all Lassie's name. Oh. Five, five, good thought. Lassie's here. Bishop. Bragg. Here. Caudill. Chestnut. Colwood. Here. Erlinson. Gerard. Green. Kennedy. Leonard. Mohammed Boy is here. Spall. Solomon. And Swisstack. All right. Seems as if the Wi-Fi is slowing up again. So let me see if I can bring up the Zoom folks. Laptop here. So for you guys out there in Zoom, I'm hoping that, well, let me know, can you hear me? Just type something in the chat. Okay, good, all right. So if there's any like indications of any lagging, I apologize. I'm recording the lecture right now, so just in case you miss anything and you want to rewatch it, I'm gonna post the link in Canvas so that you can have access to it. So the last time we were here, we were discussing nomenclature of molecular compounds. And if I remember correctly, the very last thing I told you guys to do is to attempt questions from the assignment. Let me see if I can bring up the assignment now. If I remember correctly, it was the very last page, right? Right? So let me bring it up here. Let's see if you have a good handle on how to name molecular compounds. That's assignment 2. I don't know how I did it, but I guess I printed an excess of hard copies of assignment two, so if you need one, feel free to take one from this file here. Okay, so let me scroll right down to the very last page. Okay, so let's start off with SIF4. Well, firstly, the question is asking for you to name the following covalent compound, all right? So based on the rules that we just discussed last time, and we did a couple of examples, you should be able to at least attempt these. So let me turn on my pen function here. Oh, let me do this. I apologize to you guys over in Zoom. I'm going to share my screen right now. Okay, so you guys out there in Zoom should be able to see what we're all looking at. All right, so let's start off with SIF4. So what do you think the name of this compound is? Based on the rules that we discussed the last time.
Silver.
Silver,
No, silicon.
silicon, oops. Silicon. Same thing is happening like last time. Apparently the line is affecting the checks again. And what else?
With the F4 being quadrifluoride.
F would be fluoride, but remember, when you're naming these compounds, remember you need to indicate the number of atoms of that particular element. So how do we indicate that we have 4 fluorine atoms? There's a prefix that we use. What's a prefix? Tetra, exactly. So tetra, and then what? Fluoride, not ene. Remember, the second part of the name must end with IDE for binary molecular compounds, right? So fluorine becomes fluoride, chlorine becomes chloride, oxygen becomes oxide, nitrogen becomes nitride, sulfur becomes sulfide, and so on, right? So in the case of fluorine, this becomes fluoride. So FLOURI. All right, so that's the name of SIF4, silicon tetrafluoride. Okay. What about the next one? B, N2S3. Dinitrogen. Gin. Trisulfide. I apologize for this, folks. This thing is not cooperating with me today. For some reason, the pen. Trisulfide. All right, okay. And of course, if you recall, when we discussed the rules last time, remember we said that if the first element in the formula or the name is represented by just one atom, then we do not use any prefixes for that element, right? So that's what happens in the case of the first one. But in the case of the second one, where you have 2 or more atoms represented in the formula for the first element, which in this case is nitrogen, we have to indicate that there are 2 of them. So we say dinitrogen and then trisulfide for the other one. Okay, what about C? What say you is the answer for C? HBr.
Hydrogen bromide.
Hydrogen bromide. And this is another exception to the rules that we learned, because remember I said that if you have a bimolecular compound where you have hydrogen bonded to some other non-metallic element, then we do not use prefixes at all, right? So it would be incorrect for us to name that as monohydrogen monobromide or hydrogen monobromide, right? It is simply hydrogen bromide. So this is one of those exclusive exceptions where hydrogen is involved, right? If hydrogen is bonded to some other non-metallic element. So I'm not even going to try to write that. I'm just going to tell you the answer. The answer is hydrogen bromide, all right? Okay, what about D? Bromine. Right, not bromide, just bromine. Or, and this is, I've seen this also be acceptable, you can say dibromine as well, right? So bromine or dibromine, according to IUPAC, either will do, all right? Okay, so let me scroll down. Any questions about these that we have just looked at? Any questions? Any questions? All right, so let me scroll down to number 2. Oh, shoot, let me here it is first. And then scroll down. Okay, so in the case of number 2, we're doing the reverse. You're given the names and you're asked to write the formula. So let me, I hope this works. Let me try. Okay, so for the first one, you're given diboron, hexahydride. So what say you is the formula? B2H6. All right, very good. What about B? Nitrogen tribromide. Nitrogen tribromide.
NBR3.
NBR3 is indeed correct. All right. What about C? Sulfur hexafluoride. S what?
CL6.
SCl6. Okay, very good. And then D, diphosphorus pentoxide. Diphosphorus
P2.
P2O5. Very good. All right. So if you understood what we did for the first 2 sections, then I'm going to leave you to, look at the others. If you think you have made a mistake based on what we have discussed before, you can correct it. And again, if you have any questions, you can come and see me during my office hours, either in person or via Skype. So let me clear this right now. And we're going to talk about naming, this time, ionic compounds. So let me get to my PowerPoint here. So in the case of ionic compounds, and this is something, again, you should have learned in your previous chemistry courses, introductory chemistry or high school chemistry, you should know what ions are, right? Ions are formed when you have atoms that either lose or gain electrons, right? Key thing you need to remember here, there are a couple of things you need to remember, but one key thing you need to remember is that when an atom loses or gains electrons, the number of protons and neutrons, in the nucleus will remain the same. So basically, in terms of the identity of the element, it will remain the same, but of course, now it's a different form, right? Whereas previously you had an atom, now you have an ion, which carries a charge. And the charge, of course, is due to the difference between, after the loss of the electrons, is due to the difference between the number of electrons and the number of protons present in the atom. So as stated here, in the case of a positively charged ion known as a cation, when you lose an electron, it will become positive. Why? Because now you're going to have less electrons and protons in the structure. On the other hand, if you have a situation where an atom gains electrons, then you're going to end up with a situation where you now have more electrons than protons. So therefore, you're going to end up with a negatively charged ion known as an ion. All right. So that's the difference between those two. And of course, as you should have learned earlier, ions come together, positive and negative, come together to form ionic compounds, right? So a good example of this would be sodium chloride, right? In any sample of sodium chloride, you're going to have a 1-to-1 ratio between the sodium ions and the chloride ions. And that's because, of course, the sodium carries a +1 charge and the chloride ions carry the -1 charge. And as you can see here in the structure of sodium chloride, you don't or won't have any distinct sodium chloride molecule, right? So that's one big difference between molecular compounds and ionic compounds, right? Molecular compounds exist as discrete units, right? H2O or CO2, right? But in the case of ionic compounds like sodium chloride, you don't have any discrete units of NaCl. Instead, what you have here is basically a lot of repeat units where the sodium ions and the chloride ions assemble in pretty much an ordered arrangement, and we call this a crystal structure, right? And this is a crystal structure for sodium chloride, and different ionic compounds will have different arrangements, but basically what they have in common is that you can identify what is called a cell unit, right? And you have the repeat cell unit continuing throughout the growth structure of the compound, right? So whenever you see the formula NaCl, here, NaCl, right? That is not a molecular formula, right? It's basically an empirical formula. Remember, we discussed the empirical formula earlier, right? Basically, what this is telling you is that there's a one-to-one ratio between the sodium ions and the chloride ions, right? So that's basically the big difference between ionic compounds and molecular compounds. Now, when it comes to the different types of ions, you have what we call monatomic ions. And as the name suggests, these are ions that are formed from an atom, right? And there's some common things that you can, or trends you can observe based on the positions of these particular elements in the periodic table. So as stated here, elements in group 1A, they tend to form ions with a +1 charge. Elements in group 2A, they form ions with a +2 charge. Aluminum, which is a group 3A metal, form ions with a +3 charge. And then when it comes to the non-metallic ions, in groups 5, 6, and 7, they usually have charges of -3, -2, and -1, respectively. And later on, we're going to get into the reason why we see or observe these patterns, because it has to do with electron configuration, which we won't meet until chapter 7. Also, there are a certain group of metals known as transition metals, right? And they occupy the group B position in the periodic table. So I'm talking about the elements, if you look at the periodic table over there, elements in group, according to the numbering system there. And we're going to talk about the different numbering systems later on. But according to the numbering system, as far as the groups are concerned, the transition elements would go from group 3 to group 12. So where you see scandium, which is element number 21, to element number 30, which is in group 12, and all those elements below that, they're considered to be transition metals, right? And one thing about transition metals that is very common is that in most of these cases, they can form different ions of, well, one particular element can form different ions of different charges. So for example, and I think I may have some examples here. Okay, so for example, titanium can form the titanium 2+ ion and the titanium 4+ ion. Or vanadium can form an ion with a +2 charge +3, for chromium it's +2 and +3, and so on and so forth. So we're going to see how, when it comes to naming these compounds, we can make a distinction between, let's say, a copper 2+ ion and a copper 1 ion, because that's very important when it comes to naming compounds that contain those ions. So let me scroll back up to here. So let's talk about, firstly, naming ionic compounds, and also writing formula if you're given the names of ionic compounds, right? So I would say the main rule that you need to follow, and again, this is something you should have met before, is that whenever you're writing down the formula for ionic compounds, you have to make sure that the total number of plus charges is equal to the total number of negative charges, so that the entire compound is neutral, right? So we can look at these examples to see how that works. So for the first example, you're asked to determine the formula for these compounds. Calcium chloride. Okay, what is this? It's lagging. So calcium chloride and magnesium oxide, right? So the first thing I would do, if I were you, is I would pull out that table that I gave you in Canvas, right? Because if you remember, that table gives you a list of common ions. In fact, it gives you 3 lists of common ions, right? So in the case of calcium chloride, I would go to the table and I would look up the formula for the calcium ion. And that formula is Ca2+, right? Okay. All right, imagine a plus sign, all right? Oh, here it is. And then the chloride ion, again, I will consult the table, and I will look up the formula for the chloride ion, right? And when you do that, you're gonna see it's gonna be Cl minus. Cl minus, all right? So if you look at these two ions, the calcium, it has a +2 charge, the chloride has a -2 charge. So therefore, the charges, as it is, are not the same. So you have to ask yourself the question, how do I get the charges equal? And the answer is very simple. You simply multiply the chloride ion by 2, right? So we put the 2 here, which is not sure. Oh, there it is. Okay. And then we put these together. So the final answer is going to be CaC2. All right? And that's basically it. That's how you determine the formula based on the name. So you're going to use that table in order to find out the ions and their charges. You balance the charges. You may need to multiply one or both, or you may not need to multiply any of them. There are some instances where the charges will automatically be equal, in which case you just put them together and that's it, right? Which I think is the case in B. So what do you think the answer for B is?
Mg3O2.
Mg what?
3O2.
You sure about that? Let's look at it. What's a formula for the magnesium ion?
It's balanced. This is MgO.
It's going to be MgO, but let's go through the steps. What's the formula for the magnesium ion?
+2.
+2. And what's the formula for the oxide ion?
-2.
-2, or 2 minus. So you're right. The answer will be MgO. All right, very good. Okay. Now, in the case of the next example, it's asking for the names. So it's reversed. It gives you they gave the formula and you're asking for the names, right? So what would be the answer for A? Magnesium sulfide. That's in the case of A. In the case of B, it is. Now, this one you have to be careful about. Remember what I said earlier about transition elements and the fact that they can display more than one charge. In fact, let me talk about that some more. Let's see here. Because again, this is something you should have covered before, but I need to mention the rule concerning naming compounds which contain these sort of ions, right? So according to the IUPAC rules, in order for you to indicate the different charges, you have to use Roman numerals within parentheses to indicate the charge of that particular ion. So the example that is shown here is that you have 2 types of titanium ions, right? You have titanium with the +2 charge, and you have titanium with the +4 charge, right? So to distinguish between those 2 ions, in the name, we write, in the case of the one with the +2 charge, we put titanium, Roman numerals 2, within parentheses beside it. And in the case of the +4 type, it's going to be titanium with Roman numeral 4, and then that's it, right? So when you're writing the names of these ions, make sure that you indicate the charge using Roman numerals within parentheses. Another thing I need to stress, because I've seen students make this mistake in the past. If there are ions that cannot or don't exist as having more than one charge, then no Roman numerals must be used, right? So ions like sodium, calcium, strontium, etc. Silver is another example. No, not silver. Yes, silver, actually, is another example. Cadmium and so on, zinc, those elements can only exist in the ionic form as having one specific charge. In those instances, you do not indicate the charge using Roman numerals. Okay, so let's get back to B, in the second example, CrCl3. Chromium 2, why do you say 2? Let me write
It
this
might
down.
be a 3, I can't see it.
Huh?
I can't see the letter vector, so if it's a 3.
Yeah, this is a 3 here, yeah.
I just can't see.
Okay, so the answer is what then?
Chromium 3 or.
Yeah, chromium 3, again, this thing is lagging. But yes, the answer will be chromium. So let me tell you how to write it down. It's chromium, the word chromium. Then in parentheses, you're going to put Roman numeral 3. And then outside of that, you're going to put chloride. Right? So that's basically how you name that compound, right? Now, how do you know it's 3? Well, it's very simple. If you go to the tables I've talked about earlier, you look up the formula for the chloride ion, and you see that each chloride ion will carry a -1 charge, right? So what does that mean? That means that the chromium, which is combined with those 3 chloride ions, must carry a +3 charge. So that's the reason why you know that the charge carried by the chromium is 3, and therefore in the name, you're going to indicate that in the form of Roman numerals. Okay. So let me move on to, okay, so basically what we have just discussed here is what is talked about here in terms of the rules for naming binary ionic compounds. Binary means, of course, they have 2 elements, one metal, one non-metal, and then the metal form the ions, well, the metal forms the cations, the non-metal form the ions, and then of course you have to figure out the number of each in order to make sure that the entire compound is neutral. So these items here is basically outlining the steps that we just covered in answering the previous question, which again is something that you'd have covered before in your introductory chemistry. Now, another group of ions that we need to talk about are what are known as polyatomic ions. You know what, before we do that, so let's go back to the assignment. Questions. So now, based on what we have just covered, you should now be able to do okay, so now you should be able to do numbers 11 and 12. So I want you to get on that right now. Of course, well, tell you what, let me help you with a couple of these just to get you guys started. So let's start off with this question, number 11, right? It says, give the formula and the name of the compounds formed between each pair of elements listed below, all right? So let's see, how would you answer for the first line here? Let's start off with the formula. What you're going to find helpful, of course, is the table I talked about earlier. So if you have your devices, then you can bring it up, or if you have the hard copy of the table, you may need to bring that up in order for you to refer so that you can answer these questions. So let's start off with the first one, beryllium and fluorine. So my question to you is, what's the formula for the beryllium ion and the fluoride ion? Be what? +2? That's what it said? What about the fluoride? -1, so that would be F minus, right? So how would we get the charges canceling out each other?
2 fluorides.
You're gonna need 2 fluorides. So when these put together, the answer would be BeF2. All right? So that's a formula. Yes, sir.
Should we be working on that step on the paper?
You don't have to, but I mean, yeah, I kind of figured it might help, you know, like, you know,
You won't take out points if we just build it.
right, if you just put the formula, that's fine, yeah. Okay, so that's a name. I'm sorry, that's a formula. What's the name? Beryllium fluoride. All right, so that's basically how you do that. Okay, so based on that, you should be able to do the other. But before you do that, there's one thing I neglected to mention, which is another important difference between naming molecular compounds and naming ionic compounds. And the difference is that in the case of naming molecular compounds, if you recall, we have to use prefixes in most cases. But in the case of binary ionic compounds, no prefixes whatsoever. Right? You do not use any prefixes when you're naming binary ionic compound. So for example, it would be incorrect for you to say that the name of that is beryllium difluoride. That would be incorrect. All right? It is simply beryllium fluoride because it's ionic. Right? If it was a molecular compound, then you'd have to use prefixes. Yes, sir.
So is it?
Well, the main reason why is because of what I said before. There are no discrete units of molecules in ionic compounds. So therefore, that's the reason why prefixes are not used. We use prefixes in the case of molecular compounds because you know that, for example, in one molecule of water, there are 2 hydrogen atoms. Well, not water is not a good example. Carbon dioxide. You have 1 carbon atom, 2 oxygen atoms, right? So you need to indicate, okay, You have one carbon atom, you have two oxygen atoms, so you use prefixes. But in the case of ionic compounds, you don't have discrete units, so therefore no prefixes are used, all right? Okay, so I want you to do the others, and if you have any questions, I'm here. Is Chestnut here?
Yes.
Okay. Erlinson?
Here.
Green? Check my mind. Okay, Green, Kennedy, Leonard.
Here.
And Swiss stack. Deco. Hello? Oh, you mean question 12? Yeah, you should be able to do these as well. Yeah.
No prefixes.
No prefixes, nope. So yes, 12, you guys can get on that too, and then once you finish that, then we will continue. finished or almost finished?
With the-
Let me give you 2 more minutes, because I want to move on to some of the naming rules. So, let me, continue, we can finish that part later on. Because I want to talk about polyatomic ions and how do we deal with these when it comes to writing formulas containing these ions and also naming them. So polyatomic ions, as the term suggests, these are ions that are made up of more than one atom. So these are different from the monatomic ions that we were discussing earlier. Most of them are negatively charged, but there are a couple which are positively charged. So most of the polyatomic ions are anions. And ignore that line. I don't expect you guys to commit these ions to memory, because again, you'll have access to the tables, all right? And there's sometimes some prefixes that you'll see in association with the names of these ions, like hypo and per. And this basically relates to the number of oxygen atoms that are present. Again, I won't go into the rules for that, because again, you'll have access to the list of ions. Also, in the case of most polyatomic ions you're going to encounter, their names will end with ITE or ATE. And basically, the ITE and ATE indicates that oxygens are present, all right? So this is, of course, a list of polyatomic ions along with some compounds that contain them. Again, you'll have access to the list in Canvas, so you don't need to memorize these. The list is actually more comprehensive than what you see here, but of course, you need to know how to use them, especially if you're asked to write formulas for these compounds, such as in this example right here. So this question says, write the formula for A, sodium sulfite, and B, ammonium sulfate, right? So again, you consult the table, and in the case of sodium, the formula for sodium would be Na plus. The formula for the sulfite would be SO3 minus. And then in order to make sure that everything is balanced in terms of the charges, you're going to put a 2 there for the sodium. So when you put these together, the final formula for this compound would be Na2SO3. All right. So that's basically how you name that. In the case of B, the name given is ammonium sulfate. So again, I'll go to the table. I'll look up the formula for the ammonium ion, which is NH4 plus. So this is one of the few polyatomic ions that exist as a positively charged ion, right? The ammonium ion. There are two others. One is the mercury one, and the other one is hydrogen, right? So these are also polyatomic ions, which are cations. But most of the others would be negatively charged ions. Anyway, back to this example. So the sulfate ion, if you look it up, the formula is going to be SO4 2 minus. Now in this case, you're going to need 2 of these so that the 2 minus charges will be balanced, and therefore, when you put these together, now this is where you have to be careful if you have more than one polyatomic ion represented here. You're going to put NH4 in parentheses, and then put the 2 outside, and then SO4, and that would be the final answer. All right. So you notice that in the case of the ammonium, because there are 2 of them, you have to put the formula for the ammonium ion in parentheses, and then you put the 2 outside as a subscript. All right. Okay. So in the case of the second example, you're given the formulas and you're asked to figure out the name. And again, you have to go to the table to do that. And the name of this one would be sodium cyanide. And then the name of B would be magnesium perchlorate. So again, you have to go to the tables so that you can look up the names of these ions, so you can write all the names when answering questions like these. Okay. Any questions? Any questions about this? Any questions? All right. Okay, now here's a special group of compounds that you may not have met before. I certainly did not cover it in my introductory class. These are compounds known as hydrates. Hydrates are basically ionic compounds which has as a part of its structure a fixed proportion of water molecules. All right. So what you're going to see is that the number of water molecules will be fixed relative to the formula unit represented for the particular ionic compound. All right. And basically, to name a hydrate, we would name the ionic part just as we did in the previous example. But to indicate the number of water molecules, you have to use the prefixes that you learned earlier. Mono for 1, di for 2, tri for 3, and so on. So, oh, and also, when writing the formulas for these compounds, what you need to do is write the formula for the ionic part, and then you put a dot, and then you indicate the number of water molecules next to it. We're going to see some examples of this. So, for example, in the case of this particular hydrate, you see that you have the ionic part here, which is the barium chloride part, and then you have 2 water molecules, right? So the name of this compound is barium chloride dihydrate. Barium chloride dihydrate. You have the barium chloride part, and then dihydrate indicates that there are 2 water molecules present. All right. Here's another example. Copper 2 sulfate pentahydrate. This is the formula right here. CuSO4 dot and then 5 water molecules. And this is the name, copper 2 sulfate pentahydrate. All right. So basically, it's the same thing as naming ionic compounds, excepting that you have to indicate the number of water molecules. So as long as you remember the prefixes, mono for 1, di for 2, tri for 3, and so on, then you can easily indicate the number of water molecules in association with the formula for the compound. Now, the thing about hydrates, these are very interesting compounds because one of the features of hydrates is that, and I'm going to use copper 2 sulfate as an example. So this is the formula for the hydrated form. Right? So this is copper 2 sulfate pentahydrate, right? In this context, we call this the hydrated form or the hydrate, right? And the thing about these compounds is that you can heat these to 100 degrees Celsius. And what will happen is that the water will be dislodged. So you're going to end up with copper 2 sulfate, and then the water molecules will escape as water vapor, right? Now, this form of copper 2 sulfate without the water, we call this the anhydrous form. Anhydrous, right? And what you'll find is that in terms of appearance, the anhydrous form is different from the anhydrate form, right? In some cases, and this is true in the case of copper 2 sulfate, the hydrated form will be of one color and the anhydrous form will be of another color, right? So as you can see in the picture here, the hydrated form is of a blue color, but if you were to heat it and remove all the water, then you're going to end up with the anhydrous form, which is of a white color, right? Another interesting thing about these two forms is that you can reverse this process. All you have to do is add water and you get back the hydrated form, right? And that's what's shown here, right? This is the anhydrous form, and all this person is doing is adding drops of water, and you see the region immediately becomes blue, right? Which is the hydrated form, right? So this is true for copper sulfate pentahydrate. Now, let me just say that there are some hydrates, and I will probably say most hydrates, which will not undergo color change. However, the appearance will change. In that, the hydrated form tends to have a more crystalline appearance. If you look at it like under a microscope or under a magnifying glass, the hydrated form will have a crystalline appearance, while the anhydrous form will have a more powdery appearance, right? But they'll both be white. Like, for example, in the case of barium chloride dihydrate, both forms are white, but the hydrated form is crystalline in appearance, while the anhydrous form is white. Not white, but powdery in appearance, right? So that's basically how hydrates work. And for those of you enrolled in my lab, you'll be doing an experiment involving these sort of compounds. Basically, what you'll be doing in that experiment is trying to identify your unknown hydrate based on heating the solid, driving off the water, and finding out the percentage of water that is present by finding the difference in masses between the hydrated form and the anhydrous form. So that is something for you guys to look forward to. Okay, and then we get to another group of compounds known as, known as acids, right? So let's talk about acids. What are acids? Acids are basically substances. Hold on 1 minute. Okay, let me talk about the different properties of acids and bases first, and then we get into the definition. So as you can see here, there are some properties listed of acids. First one says taste sour if diluted with enough water to be tasted safely. And let me just say that nobody should be tasting any acids in the lab, so don't get any ideas about doing that, right? I have to say that because I've had students actually try to do that in class, right? May produce a pricking or stinging sensation on the skin, right? Again, please don't dip your finger in any solution of acid in the lab to find out if that is true, right? Here's an important property. It turns the color of litmus paper from blue to red. Now, I don't know if you're familiar with litmus, but litmus is a substance which takes on a particular color depending on whether or not its aqueous environment is acidic or basic, right? So the color of litmus is red in acid and blue in base, right? So as you can see here, it says it turned the color of litmus from blue to red. And you know, litmus can come in the form of a solution, but you can also have it in the form of a paper. In other words, the paper is soaked with litmus, and you just take that paper, usually it's a strip of paper, and you dip it in the solution. And if the litmus was formerly blue, and you dip it in the solution, becomes red, then you know that your solution is acidic. Okay, the next one is acids react with many metals to produce ionic compounds and hydrogen gas. And that is particularly true for the more active metals like the ones in groups 1 and 2, and maybe some of the other transition metals, all right? And then the final property listed here is that acids react with bases, which we're gonna talk about later on. And what happens when the acid reacts with the base is that the properties cancel with each other, so you'd expect the product to be neutral. All right, so those are the properties of acids. And then as far as bases are concerned, they tend to taste bitter if, again, diluted in enough water to taste it safely. Again, these do not taste any bases in the lab. Feels slippery or soapy on the skin. Again, do not, dip your fingers into any base to see if that's true. But let me just say something here. The reason why that is observed is because when the base lands on your skin, there's actually a reaction that takes place between the base and the oils that are produced by your skin. And the result of that reaction is, believe it or not, soap. So that's the reason why it feels soapy and slippery when it comes into contact with your skin, all right? In terms of the effect on litmus, it turns red litmus blue, as I described earlier. Reactant acids, as I said before, we call that reaction a neutralization reaction. And as a result, the basic properties will be canceled out by the acidic properties, all right? So now we're going to get into the definitions of acids and bases. And the definition that is used is dependent on who you ask. Now, this guy here, by the name of Arrhenius, he came up with his definition of acids and bases, right? According to the Arrhenius definition, an acid is a solution or is a substance which, when added to water, ionizes to form hydrogen ions and some other anion, right? While an Arrhenius base is a substance which, when added to water, forms hydroxide ions and a cation in solution. So that's the definition of an acid or base based on the Arrhenius concept, all right? And for those of you who have to do Chem 2, you're going to learn that there are other definitions of acids and bases as well. But I won't go into that right now, all right? But now we're just going to be satisfied with what we have here. And neutralization, I kind of alluded to it earlier. That is reaction between an acid and a base to form water and a compound known as a salt. And the composition of that salt is based on the composition of the acid and base that you're going to react in order to form this salt. All right. What is a salt? A salt is the combination of the cation, which comes from the base, and the anion, which comes from the acid. All right. So that is basically a summary of the Arrhenius concept of acids and bases. And I think, I thought there was an example of neutralization there. Anyway, so let's talk about how we name acids. So it turns out there are several approaches one could take in terms of learning how to name acids. I'm going to start off with the binary acids first, right? So let me, okay. So the name of the binary acid, well, firstly, what do we mean by binary acid? Binary acids are acids which are made up of hydrogen and one other non-metallic element, right? So hydrogen combined with a non-metallic element. Now, how do we name these binary acids? Well, one approach we can take is that we can name it based on the anion of the non-metallic element which combines with the hydrogen. So, for example, let me get this. On the slide. Okay, so if the name of the monatomic ion is, let's say, chloride, the formula is, okay, let me write the name first. The name is chloride, right? And the formula of the chloride is Cl minus, right? So that's the name of the anion. Now, to get the corresponding acid, we need to add H plus to this, right? And H plus added to this will give you this compound. Now, this compound is known as hydrogen chloride. Hydrogen chloride, all right? Now, hydrogen chloride exists normally as a gas, right? Now, if you add this gas to water, you're going to end up with HCl aqueous. Now, this in an aqueous solution, the name of this, it will be named as an acid because this solution is now acidic. And the name of this acid is hydrochloric acid. All right. So please note the differences between this name, and this name. The chloride ion is simply this, right? Cl minus. Hydrogen chloride is what is formed when H plus is added to the Cl minus. You're going to get HCl, which is in the gaseous state. But when you add that to water, the solution now becomes HClAQ. That's an acidic solution, and the name of this compound is, or the name of this solution is hydrochloric acid, right? And using this example, you can see that this name is, how should I put this? The arrangement is similar to the name of other binary acids, in that all binary acids starts off with hydro, then the stem of the name of the other element, then ic acid. All right. So let me give another example. Bromine. Right? Br minus. Oops. Then you add H plus. What does that form? HBr, which again is a gas, if I'm not mistaken. Right? The name of this compound is hydrogen bromide. All right. When you add this to water, it now becomes HBr aqueous. So what do you think the name of this acid is? Hydrobromic acid. Exactly. Hydrobromic acid. All right. So let me do another example. Sulfide ion. I'm sorry, I should have written down the name first. So sulfide. All right, S2 minus. In this case, you have to add 2 hydrogen ions. Why? Because you have a -2 charge right here, right? So the name, the formula becomes H2S, again, this is a gas, and the name is hydrogen sulfide. Right? So when you add water to this, or add it to water, what do you think well, this becomes H2S aqueous. All right? So what do you think the name of this compound is? Hydrosulfuric acid. Acid. All right? Okay. So that's basically how you name binary acids. All their names start off with hydro, then the stem of the name of the other element, and then ic acid. Hydrobromic, hydrochloric, hydrosulfuric, hydrosilenic, all those acids, that's how you name them, all right? So those are binary acids. Now, the other types of acids that you need to be aware of, can I hear this? Okay, so the other type of acid we need to be aware of are the oxyacids. And the thing about these acids is that they contain, as the name suggests, oxygen, hydrogen, plus one other element. All right, so all oxyacids must contain hydrogen, must contain oxygen, in addition to another element, all right? Now, how do we name these acids? Well, we can start, as we did before, with the names of the corresponding anions. So I'm going to get into a couple of examples illustrating this. So, NO2 minus, all right? The name of this ion is a nitrite ion, right? Now, if you add H plus to this, you're going to get HNO2. So the corresponding name of this acid that is formed now is called, and please make a note of this, nitrous acid. Right? So basically what happens is that the ITE ending of the corresponding anion is replaced by OUS acid. All right? Well, let me give another example. SO3, 2 minus is known as the sulfide ion. Right? To convert this to the corresponding acid, because you have a -2 charge here, you need to add 2 H plus charges. So this becomes H2SO3. The corresponding, I'm sorry, SO3, not 4. So this is 3, right? And based on what we did here, what do you think the name of this acid is? If nitrite becomes nitrous, what does sulfide becomes?
Sulfurous acid.
Sulfurous acid. All right. Okay. So basically, if the name of the anion ends with ITE, then the name of the corresponding acid ends with OUS acid. All right. Okay. However, there are also ions whose names do not end with ITE, they end with ATE. So let's deal with that one right now. So I'm going to erase the 2 here and the 2 here. And let me just erase the names here, all right? So what I'm going to put here is a 3 here. And this is known as a nitrate ion, right? So if you add H plus to this, you're going to get HNO3. And the name of this acid is nitric acid. Right? So you see here is that in the case where the anion here ends with the ATE ending, the corresponding name ends for the acid, ic acid. All right? So let's see what happens in the case of here, here. So I'm going to put a 4 here, right? Now the name of this ion is sulfate ion, right? So that's the formula for the corresponding acid. So what do you think the name of this acid is? If nitrate becomes nitric, then what's the name of the acid formed from the sulfate ion?
Sulfuric acid.
Sulfuric acid, exactly. So that's basically how we name oxyacids, right? So to summarize, if the name of the anion ends with ITE, then the name of the corresponding acid ends with OUS. If the name of the anion ends with ITE, then the name of the corresponding acid ends with, ATE, the name of the anion ends with ATE, then the name of the corresponding acid ends with ic acid, all right? Now, there's one particular acid which is very unique because it does not fall under the category of binary or oxyacid. And that acid is HCN aqueous, all right? Now, that can be formed as a result of adding hydrogen cyanide, which is a gas. And by the way, this is a gas that you don't want to find yourself in a room filled with that gas. It won't last long. So if you add HCN to water, you're going to get this. Now, this is called hydrogen cyanide. So what those wise folks at IUPAC decided in terms of cyanide, in terms of naming this as an acid, is that we treat this as a binary acid, even though it's not a binary acid, right? Because obviously it has 3 elements in it, right? So according to IUPAC, the name of this acid is hydrocyanic acid. And that's it, all right? So that's a bit of a unique kind of situation, right? But as far as the other acids we learned, basically you can just follow those rules when it comes to binary acids and oxy acids, all right? Okay, we're gonna stop here for today. So now you have everything you need in order to complete assignment number 2. So what I'm gonna do is, and before you leave, I have another announcement to make, but let me deal with this first. I'm going to open up a Dropbox for assignment number 2 right now. Actually, hold on. Oh, that's a different date. Okay, so let me decide on what date. So today is the 23rd of January, 2025. Hmm?
You're into 2026.
Oh, shoot. There. Way into the future. Okay, so that's today, right? So this will be due on Monday at midnight. We made this a bit more specific. Now. Today. Okay. So please note, it's due on Monday. So. Oh, what do I do? What does that mean? Oh, oh, that should be fine. Oh, this should be, okay. So, okay, now everything is straight, all right? All right, so please make a note of the due date for that. The second thing I want to talk about before you guys leave, I'm quite sure you saw the announcement about advertising the event sponsored by the STEM Club. Talks about STEM careers, information about that would be disseminated in that event. It's going to be at the Ocala campus. And unfortunately, I did not include in the flyer the Skype link, not Skype, I'm sorry, Zoom link for that event. I will post that in Canvas so that if you don't want to make it up there, Ocala, you can join us via Zoom. And if you're interested in a STEM career, not necessarily like, medicine or pharmacy or whatever. But if you're talking about, biomedical engineering or any math-based, type of career, like actuarial science and so on, then I would strongly recommend that you come and attend that particular event. And also, I want to extend this opportunity for you to join the STEM Club if you have not done so already. We have a STEM Club, which basically covers all the campuses. And basically the purpose of the STEM Club is to, encourage and introduce students to different possible STEM careers. In addition to the event that will be held on the 5th of February, I'm trying to make an arrangement to have a field trip to a facility in Pensacola called the Institute of Human and Machine Cognition. I've been there, the STEM Club went there a couple of summers ago, and it was a very interesting experience. I'm quite sure you'll find it fascinating. A representative from that organization, she will be attending that event as well on February 5th, and she'll be talking about internship opportunities available at that company. And I would think that, you might find that useful as well, because one thing about what they're offering is internships for anybody in STEM field. It doesn't matter what the discipline is. So you may want to take advantage of it, because that might look good for you, especially when you apply to, transfer to other schools or grad schools and so on, right? So I just thought that, you should be aware of that event, which will be on the 5th of February. So not next Wednesday, but the other Wednesday, all right? Okay, so that's it, folks. I'll see you guys next Tuesday.
What kind of process is joining the STEM club?
Oh, just send me, just send me an email saying that you're interested, and I'll put you in the STEM club campus, and then you'll have access to
Awesome.
the information, yeah,
Yeah, thank you.
because all I need is your name and ID number.
Okay.
Yes,
So I'm in the Ocala class for your
Okay,
live, but I've been attending the one here.
Oh, really?
yesterday. Yeah, I was at your one yesterday,
oh, okay,
and I submitted the safety quiz in that class. I'm not sure if you already graded it or if I've been getting credit,
interesting. I think I do remember,
because I remember asking you in the beginning if I was allowed to.
right,
alternate.
I think I left it in my other office at the time. Because I remember I was grading, I was putting in the grades. And I realized that there was one paper that was not. There's a name that was, let's see,